All right, question number 6 asks, how does carbon dioxide cause a decrease in the affinity of hemoglobin for oxygen? All right, there are really two ways in which it does this. All right, we'll cover actually reason 2 first. The N-terminus, some of the amines on hemoglobin, or NH2 groups, or NH groups, are capable of getting carboxylated. So they can actually bind to a carboxylate like so, or to a CO2. You can form a bond with CO2 to form a carboxylated amine. And these carboxylated amines then are going to change to the charge of the N-terminus of the protein and create new types of bonds. Well, the new bonds that are created in the presence of CO2 like this are characteristic of, they basically kind of lock the protein into the T state. All right, so one way in which CO2 causes a decrease in the affinity of hemoglobin for oxygen is by carboxylating the N-terminus of the protein, which causes conformational changes that lock the protein into the T state. All right, the other way is, this is kind of a precursor to number 1, increases in CO2 concentration lead to decreases in pH. And we talked about how CO2 reacts with water to form carbonic acid. So basically, high levels of CO2 equal more acid, which equals lower pH. Now, why does lower pH matter? Well, one of the things that, so if we compare the T state to the R state, right, the T state of hemoglobin basically binds more protons, right? And we talked about one example of this. There's a histidine in the T state. So this is all in the T state here of hemoglobin. There's a histidine NH, the positively charged part of histidine. I'm not drawing the whole thing here. On the side chain is really close to a carboxylate, I believe from aspartate, if I recall correctly. All right, now the proximity of this aspartate to the positive charge of the histidine causes the pKa of this histidine to increase. Right? If you wanted to look at the prediction of that, so normally pKa is about 6. Right? If we're less than that, the side chain is positively charged. If we're above it, it is neutral. Actually, sorry, not negatively charged. All right, so we want to increase on the pH scale. So this is basically a drawing of the pH scale. The side that is favorable here. So a positively charged histidine is favorable to be next to a negatively charged aspartate. So as a result, the pKa is going to increase. Well, what does this do? It's basically increasing the pH values at which histidine is going to be positively charged. All right. So hopefully, this is maybe obvious to you. There's ways of showing it with thermodynamics. I don't want to go into that right now, but hopefully you can see that if there are more pH values at which histidine is going to be positively charged, that means that histidine now binds protons more tightly, right? And there are other examples of sites in hemoglobin where this is also true. So in general, the T state binds excess protons that the R state doesn't. Right now, I'm showing you that up here in this equilibrium. So the T state basically has these extra protons bound. This is kind of a T state proton complex with X protons bound. All right, now we know that the T state can convert to the R state, right? So I'm drawing this reaction up here on the top. The T state with its protons bound going to the R state. Now, in the R state, those excess protons that are bound are released because the R state just doesn't require them anymore because of its conformation. All right, so as a result of this, these protons are released. Well, now let's think about this. All right? An increase in CO2 concentration causes a decrease in pH. Decrease in pH means that there are more protons. So we're increasing the amount of protons. All right, well, by Le Chatelier's principle, which way does this reaction shift? Well, it's going to have to shift to the left. All right, if we're increasing the amount of products, the reaction is going to shift to the left, which means that the R state is going to shift towards the T state. And the T state, as we know, is the state that binds oxygen more weakly. So this is the second reason why CO2 or how CO2 causes a decrease in the affinity of hemoglobin for oxygen.